So first, let's start with the Apache Sedona introduction and overview. So as you already know, Sedona is the most popular open source cluster computing engine for big geospatial data. We have our website at sedona.apache.org and our GitHub also under Apache organization. We have our social media account on both X and LinkedIn. So be sure to follow us on social media to get the latest news of Sedona. And the overall downloads of Sedona has exceeded 50 million. There are actually over 150 contributors on GitHub right now. And many people are using Sedona in production, and including logistics, financial services, and agriculture as well. And here is a brief overview about the ecosystem in Apache Sedona. So Sedona mainly has multiple layers. So the first layer is what we call spatial query processing layer. So in this layer, we provide spatial SQL, Python, and Java API for the users. And it also integrates with a number of developer tools, including Apache Zeppelin, Tableau, Jupyter Notebook, and GeoPandas. This layer also equips with a number of distributed spatial query algorithms. The query optimizer will automatically decide which query algorithm to use given a particular query and dataset. And after that, Sedona has this distributed spatial dataset layer. In this layer, it equips with a number of technologies that actually use up the data structure for the fast query processing. First, it has the spatial data partitioning and the spatial data indexing and the spatial data serializer. And finally, Sedona can run on top of a number of distributed query engines. It can run on top of Spark for batch processing, on top of Flink for stream data processing, as well as Snowflake. By far, our support on Spark is the most comprehensive one. And the Sedona release follows the 3 months release cadence. So we actually made a new release last month, so which is Sedona 1.8 release. There are lots of exciting features included in the 1.8 release. And actually last month, we also announced 2 new projects, SedonaDB and Spatial Bench. Both are sub-project of the Apache Sedona project. And in particular, for SedonaDB, we can also follow a particular release cadence. Right now, since SedonaDB is a new sub-project, so we are receiving lots of new contributors and lots of patches. So we are expecting that release cadence to be more frequent, which will be around 1 or 2 months release cadence. The next release of SedonaDB is coming up soon. It's going to be sometime around this month in November. Please stay tuned. And today we have interesting talk from a Sedona contributor, Jess. She will talk about the CIS transformation in SedonaDB, which is a new feature we released last month. Welcome, Jess. Please take over.
All right, thank you. Going. All right, is that sharing? Can everyone see the slides?
Yes.
Excellent. All right, well, I'm Jess, and I'm going to walk you through coordinate reference systems and transformations in SedonaDB, which is a topic that's fundamental to getting accurate spatial analytics at scale. I will briefly go over why we care about CRSs in general, and then dive into some of the technical details about how CRSs are defined within SedonaDB, how Sedona enforces CRS consistency, and then the transformations that allow you to move from one to the other. And then we'll have a quick discussion about what's up and coming. So let's start with the basics. A coordinate reference system is essentially a framework that tells us how to interpret coordinate data in space. Each one has a datum, which is the origin for which the CRS is defined, the units, such as degrees, meters, or feet, and the projection method. These are very important so that we can get accurate locations. Without it, you could be off by hundreds of meters or more. You also need it for meaningful analysis, for spatial joins, overlays, and distance measurements. They only work correctly when your data is properly aligned. It prevents costly errors by mixing degrees with meters or different projections, and it allows for interoperability. Finally, it supports local needs. You can use global systems like WGS84 for worldwide analysis or local projections like UTM for high precision regional work. So in SedonaDB specifically, we attempt to carry over any CRS information that is already available. For example, in the file like GeoParquet, we try to parse that information immediately. And whatever way you're getting the information in, try to get that in automatically so that it's correct. For example, from the GeoParquet, we can pull this CRS information directly from the metadata. However, if it has not been set, SedonaDB provides both the standard ST-set SRID, which assumes EPSG code authority and allows you to void the CRS with that zero code. But SedonaDB also introduced set CRS as a new function, which allows for much more complex CRS identifiers because you can use different authorities, not just EPSG. And additionally, you can use full JSON for maximum flexibility. Sedona supports, this allows you to define custom, complex, or non-standard coordinate systems. You can describe local projections, compound CRSs, or even specialized systems that your organization uses. The JSON format follows the Proj JSON standard. And it's a bit verbose, but it's very powerful. Under the hood, we're using Proj, which is the standard library for coordinate transformations. We leverage Proj for both defining the CRSs and doing the transforms between them. And this allows us to have very precise spatial analytics with interoperability. And Proj comes standard with allowing for thousands of defined coordinate systems. We also have CRS-aware operations. This enforces that the two different geometries are in the same CRS before attempting the operation. And if it finds a mismatch, then it will error to allow you to make the change. So what do you do in that case? You need a CRS transform. So again, we're using Proj to do these transforms. And the basic steps to do a transform, you need to first find the transformation from your source CRS to your destination CRS. And then we use Proj to transform each of the individual points within the geometry. So there are some performance considerations there, definitely. The initial transform generation is very expensive. So we are caching that on the first one that we do, and then using that for all of the following geometries, assuming that they are using the same destination and source transformation. So some simple examples, you can use either the SRID to define the CRS or some JSON. So what is next? Currently, the CRS definitions are sitting on the entire column, and we are going to move that towards a row by row definitions. Furthermore, we'd like to support grid shift files like NADCON and NTV2. These files provide local datum corrections for sub-meter precision, which is crucial for engineering, surveying, and government applications. And Finally, we're looking towards CRS support within rasters. This is up and coming, which means that the rasters will interact correctly with vector geometries for operations like clipping. And what is pretty much it. So in summary, Sedona offers flexible, robust CRS management for scalable spatial analytics. We have multiple options for CRS specifications, SRID, JSON, custom definitions. We have CRS-aware spatial operations, which ensure correctness, and easy transformations through the Proj library integration, giving you precision that you need. And we're advancing towards even more powerful features like per-row CRS and raster support. So Sedona takes the complexity out of coordinate systems while ensuring your spatial analysis is accurate and reliable. And that's it. And just have a little link to some examples there that are in our blog.
That's it, Jess?
That is it.
Cool. Great. Thank you. All right. There are some questions. Is the projection considered on spatial index? So if this is about SedonaDB, right now the projection is not considered as on the spatial index. The spatial index right now used in SedonaDB itself only factor in the only consider Cartesian space, so which treat everything as 2D. It doesn't consider the projection. Yes, same for partitions. For partitions, both spatial indices and partitions. So we don't consider right now. We don't consider projections. We treat everything as geometry, as 2D Cartesian geometries. All right. I have a few more slides. As you know, we have a book for Apache Sedona, and this is going to be out really, really soon. And we also actually have some early release version of this Apache Sedona O'Reilly Animal book. So if you are interested, you can get a free copy through this URL. You can also search on Google by typing Cloud Native Geospatial Analytics with Apache Sedona. You'll be able to find link and you will be able to get a free copy. And as always, Sedona is always calling for help. So if you are willing to help, if you're interested, contribute to Sedona, including documentation, examples, and also participate in the release test, feel free to chime in, GitHub repo, and also on our mailing list. And I think that's all I want to share today. I'll stay here just in case if you have any questions. Feel free to post your question in the chat and also in the Q&A session here.